Okay, so thanks everybody for coming and joining us this afternoon. We're Atmos International. We're here to talk to you about using high resolution data to detect when and where water leaks occur. We'll start off just doing some introductions. I'm Martin Duff. I'm Business Development Director for Atmos. I'm here. I've joined Atmos sort of in the last year with the remit of leading our entry into the water space with our leak detection solutions. Atmos are predominantly operate in the oil and gas sector, so water is a relatively new thing for us. So we'll go into that as we go through the presentation, and I'll pass you on to Harry.
I'm Harry Smith. I'm a sales and senior research engineer at Atmos. I've been here now over 9 years, as well as managing sales territory around the world. I work very closely with the R&D team. We're working very closely with Martin Duff to move our technology into the water industry. Hope you look forward to this presentation.
Okay, guys, and just a reminder for those of you who've just come through, if you could keep yourselves on mute and your cameras off, and if you have any questions that you would like to ask as we go through, just pop them into the chat and we'll address them at the end. Alternatively, you can stick your hand up at the end. We have a Q&A session after the presentation. Okay. So just to introduce really leakage in the water sector from a UK water perspective. I mean, leakage reduction in England and Wales has been a regulatory requirement since 1997. After severe drought in 1995 left reservoir levels very low, but it has been a primary focus of water utilities' attention for the last 5 to 10 years. It's fair to say it's been very much on the front of the forefront of water utilities agendas. In 2019, the water companies in England set themselves a goal of halving leakage by 2050 and tripling the pace of leakage reduction, achieving this decade by 2030, the same level of improvement that had previously taken 30 years to achieve. Current AMP7 leakage performance commitments expect water utilities to realise, on average, 15 to 20% reduction in leakage by the end of the AMP. Of course, that varies a little bit outside of that range between different water utilities, but 15 to 20% reduction by the end of the AMP period, and that's obviously quite a stretched target. So this accelerated effort will save almost 1 billion litres of water per day by 2030. That's around a third of current losses, putting us on track ultimately to halve leakage by 2050. With nearly 350,000 kilometres of ageing pipeline, this will be an enormous challenge, as we know. Following on from the leakage commitment made in 2019, last year Water UK, which is a membership body made up of the UK's water companies to represent the water industry, they produced a 2050 leakage route map, which provides the whole sector with a framework for action as water companies build their water resource management plans for the coming decades. There are many angles covered in that framework, and a number of dependencies were stated, such as regulatory and government support, step change in the replacement of old pipes as we run out of active leakage control options, more collaboration with supply chain, local authorities and between water utilities. But the 2050 leakage route map appears not to address one key consideration, which is the quality of data. The volume of available data in the water industry is at an all-time high. Water utilities have invested heavily in metering in a bid to produce better outcomes, such as reducing water leakage, minimising water supply interruptions, and mitigating the damage caused by any pollution incidents through the use of data. However, the quality of that data that exists is not as good as it could be. Technology communication advances such as IoT, Industry 4.0 and big data allow data to be collected at high resolutions never previously possible, yet water utilities often don't maximise the full potential of the data that is available to them. In some cases, multiple filters and interpretations are applied to data which is collected either inaccurately or too slowly, so the meaningful interpretation of that data can get lost, or even worse, be misleading. This could have a large impact on the actual outcomes that the data interpretation provides, costing time, money, and risking interruptions in service to customers. So just to introduce you a little bit about Atmos International, we're a pipeline technology company that focuses in the oil, gas, water, mining and aviation sectors. Oil and gas is very much our bread and butter. That's where we were founded. We were founded in 1995 after our CEO invented leak detection products whilst working and undertaking a PhD with Shell. And we're considered the world-leading company for leak detection and theft detection in the oil and gas sectors. We act as preferred partners for most of the household brands that you'll all be aware of, such as ExxonMobil, TotalEnergies, Shell and BP. So we've got really good credentials in the oil and gas sector, and we're moving across into the water side of things. We're also keen to point out we're a proprietary manufacturer of leak and theft detection hardware and software products. So we have full control over the full end-to-end solution from a hardware and software perspective. And we currently monitor over 1,500 pipeline networks worldwide, some of which are tens of thousands of kilometers long. So whilst our technology was developed in the oil and gas sectors, it's also applicable to water applications too. There are some differences between water networks when compared to oil and gas networks. You can see a lot of these in the table in front of you. An example of this is the fact that the entire water pipeline network is typically buried underground, compared to oil and gas, where the pipelines are often above ground, and particularly where they are near assets. So that presents a challenge around the process of installing leak detection instrumentation. In contrast to the oil and gas industries, access to power and comms in the water industry is limited because large lengths of water network do not currently attract the investment of power and communications. So this places a limitation on the leak detection solutions available to a water pipeline operator, as represented by the fact that there are many areas of the water pipeline network that currently have no leak detection coverage at all, such as further upstream trunk mains and also rising sewer mains as well. Whilst there are key differences between oil and gas networks and water networks, the requirements of an effective internal-based leak detection system remains the same. So you can see on here, it doesn't really matter what sector we're looking at. Any leak detection system needs to have a high sensitivity so it can detect ruptures instantaneously. You want to be able to detect each and every leak or theft, and be accurate in understanding where that leak is located. The system has to be quick to alarm, and also have no false alarms with it. You need to have the right level of confidence in the technology that's being put in the ground. And alongside that, on a more practical level, it has to be easy to retrofit, and you have to be able to operate it and maintain it nice and simply as well. Otherwise, it just won't get the longevity that you need out of a system like that. So having a look at what we've done in Atmos in terms of modifying what we have and taking what we have in oil and gas and being able to apply it to the water industry. Starting off there with the desired features, we mentioned in the last slide, low entry cost, low running cost. That's really key because of the complexity and size of the water networks. It's really important that the entry cost and ongoing cost of maintaining that system are low. Otherwise, you'll just never get those solutions up off the ground. Non-intrusive pressure and flow instrumentation is the preference because of those issues that you have with comms in much of the water sector, where the comms just isn't there. But also improving the retrofitability aspects means that if you can have non-intrusive pressure and flow, then you're much more likely going to be able to adopt this system on a network scale. Likewise, where you have a lack of power, then having battery-powered solutions so you can deploy your instrumentation anywhere along the network gives you a real advantage and opens up the possibility of where along the network you can undertake effective leak detection. Looking at the target areas within the water sector, of course, networks are complex and they are split into different sort of categories, different areas. We look at trunk mains and rising sewer mains in particular. Those are two areas which are very much underrepresented at the moment from a leak detection perspective. So that's an area that we've decided we'd like to approach. But also the DMAs, so the district metered areas that you have at the moment, obviously towards the bottom of the network, that's where most of the activity is already in terms of leak detection solutions. Because the way the technology works is picking up on drops in pressure and flow and changes in flow. It doesn't mean that we can just undertake leak detection. We can also look at other operational conditions and other things that might be going on in the network. So we can undertake things like inter-reservoir analyses and drain down analyses as well. As part of that, we can also look at air valve analysis as well. And looking at the methods, and I'll hand over to Harry in a second, who'll go into more detail about the actual techniques we use. But looking at all of the armory of tools that we have available here at Atmos to undertake leak detection, the methods that we feel are most appropriate to bring to the water sector are looking at noise correlations. That's obviously your acoustic logging, which helps you to find existing leaks. But then looking at flow balance and volume balancing as well, so you can look at small differences over large networks and large periods of time, and effectively look at background leakage. And also shut-in pressure analysis, and the important one really is our pressure wave technology and being able to process that at the edge using 60 hertz data. That's obviously sort of the main reason we're here today, is looking at that high quality data, which we'll go into in a second, which refers to really collecting 60 hertz data and doing something more meaningful with it. So with that, I'll pass over to Harry, and he'll start talking a little bit more about the algorithms and stuff that we use.
Brilliant, thank you, Martin. So yeah, as Martin was saying, today's talk is showing you the importance of using data in the right way, specifically for pipeline leak detection. So what we're going to cover in the next few slides is the software package that Atmos provides and why is it so important to sample at that high acquisition rate. So the leak detection software that we apply to pipelines is what we call the Atmos Waveflow technology. So it incorporates multiple methods, but two main methods. The first method is what we call the negative pressure wave. Now this identifies the negative pressure wave when a new leak, burst or rupture occurs on the pipeline. And this will propagate through the pipeline around the speed of sound, and it will be detected by installed pressure sensors and data acquisition units that are sampling at 60 samples a second. And because we'll be GPS timestamping each piece of data, we can then provide a very good, accurate point of origin. Now, if you can install flow meters or you have flow meters available on your pipelines, then we can combine this with an intelligent flow balance. Now, what's useful about utilizing flow meters is it allows you to detect new leaks that might be forming over a longer period of time, but also you have the advantage of being able to detect existing leaks on your network. If you can put more instrumentation down the pipeline, so the more hardware you have, the better the performance of the system, you can then do pressure distribution analysis. And then when we talk about pipeline leak detection, especially when we're looking at the internal properties of the pipeline, so flow, pressure, temperature, it has a very unique pattern to it. So when our technology detects these changes in flow and pressure, we can alarm very quickly. So what you're seeing here is the negative pressure wave principle happening. So what you can see as a leak occur and the negative pressure waves traveling up the pipeline. So we have installed PTs, they'll be sampling at that high acquisition rate, and we're able to see that small change in pressure associated with that leak and provide an accurate leak location from that. Now you have the advantage, especially when we're talking about the water industry, is that I know it's very important to detect your existing leaks on the pipeline, but more importantly, you need to be able to detect these new leaks forming so they don't just add to the pot of existing leaks. But let's look a little bit deeper into the importance of why we sample at that high acquisition rate and what it gives us in terms of information for a leak detection system. What we're seeing here is 4 graphs, and I'll just go through them. So the top one on the left is showing data in a DCS or SCADA system being sampled at between 1 to 5 seconds. And what we're seeing to the right of that is the same data, but being sampled at 60 samples a second. And this is the importance of utilizing data in the right way, is that if you're not sampling the data at a high enough rate, you might miss changes on the pipeline that are actually quite important. That could be related to a leak, it could be related to pump issues, you might even have passing valves. If any of you spent time in a control room, we're now looking at the bottom left image, often you'll see a SCADA system like this where the pressures are on a similar scale. Unless you're looking at the pressure all the time, you might miss very small changes associated with the potential of a leak. And this is why our technology is collecting that data at such a high acquisition rate. We want to see these very small changes in pressure that might indicate a new or existing leak present. And this is the problem. A lot of water industries, I'm sure, are on a mission to get as much data as they can from the pipeline, but a lot of these are only transmitting data, let's say, every 15 minutes, every 5 minutes, and it might not be at the acquisition rate you need to be able to see clear changes in pressure of flow associated with new or existing leaks present. Let's look a little bit more deeper again. So this is a screenshot. This is from an engineering window that we use at Atmos. The top trend is we're looking at pressure data on a similar scale, what you would expect to see in a control room. And what you might notice is that there's a very small change in pressure associated here, but unless you're actually looking at it all the time, you'll more than likely miss this at the sample rate of a SCADA system. At 60 hertz, you'll be able to see this very small change in pressure. And as Martin mentioned, using the algorithms that we have available to us, we can pick up these very small changes in pressure and then provide a leak location. The advantage of picking up a leak early means it's not going to develop into a larger leak. This leak we're actually looking at now is only 0.2 bar change in pressure. So it's a very, very small change in pressure compared to the overall line. Another example we've got, and this is a genuine leak detected on a water pipeline in the UK. So what we've actually got here on the left is the data provided by the customer, where they were collecting data every 15 minutes. Now, what we can see here is this pressure drop here represents the same pressure change we've got here. And what this was an air valve failing. And when the pipeline was shut down over a long period of time, the pressure slowly started to fall away at quite a significant rate, and it triggered a low pressure alarm. But what's being missed in the 15 minutes data is the actual start of the leak here, which we've highlighted in the green circle. Now, this is being picked up because our system is sampling at that high acquisition rate. So we were actually be able to provide an alarm much earlier than their existing SCADA system would have been able to detect the change, highlighting that you'd be able to detect the leak faster and hopefully reduce the potential risk that this might occur. Going into a little bit more detail on this leak. So we're now looking at our engineering window again. So this black trace is showing pressure data, and what we can see is the pipeline is operating and shutting down. And as I noticed from the previous slide, from the 20th of December onward, we started to see a significant pressure change when the line was shut down. So the pressure was falling at a much more significant rate than it should have. And based on the data analysis we were able to do, so we knew where our pressure transmitters were assigned, we knew the pipeline length, and we knew the high point of the pipeline itself, we were able to provide an estimated location based on the reflections of the pressure wave. We gave an estimated location. The customer went out to review the location, and it actually turned out to be an air valve leaking. And we were able to provide a very accurate leak location of plus or minus 10 meters from the actual location. And it just shows you, this is just reconfirming why the negative pressure wave is such a useful technique, because it's one, it's a very fast response time, and two, it provides a very accurate leak location. And we're enhancing that further with that 60 hertz data, which allows us to see very subtle changes in pressure. But we can only get so far with the software. As Martin mentioned, you need to be able to have hardware in the right place to be able to collect the data you need to then provide a reliable solution. And this is where it becomes slightly more challenging when we talk about the water industry. A lot of the pipeline is buried. There's only limited access where you can put instrumentation, and sometimes communication and power can be a challenge as well. So what we've done is we've developed a range of solutions that can help us mitigate those potential issues. So the first one is our data acquisition unit, and at the left, which we call an AWAS unit. This can be installed at your pump stations or your reservoirs or at the ends of your pipeline where you might have pre-existing instrumentation such as pressure and flow meters. It's a very simple device. It connects to your instrumentation via a 4 to 20 output, And what it does, it takes an analog signal, digitalize it at that high acquisition rate, and then with GPS timestamping each piece of data. What we've also done is we've developed a range of non-intrusive solutions that we call the Eclipse. So this will clamp around the pipeline itself and allow us to collect non-intrusive pressure, flow, and temperature. All the circuit boards are included into the body, so that means it's sampling that data at a high acquisition rate. It's got a built-in GPS antenna, and it also can work with an array of communication options, so 3G, 4G, radio link, or it can tie into your existing network. This also has the ability to be buried, but we did originally develop this for the oil and gas. So it is, as you can see in the picture, very well engineered, and it needed to be ATEX certified. We are working on a variation of this for the water industry, where it's going to be slightly more compact, but it's going to still have that solution of being able to provide a fully non-intrusive capabilities. And finally, we have the Atmos Aquarius. Now, this is a device that's been purpose-built for the water industry. So what it allows us to do, firstly, it's battery powered. It allows us to connect to existing hydrant or air valve locations and allows us to sample pressure and hydrophone data. If we have enough spare space on the pipeline, we can actually install a non-intrusive flow meter as well. And what the advantage this Aquarius has, it allows us to put instrumentation in very small locations, and it allows us to put the hardware where we need it. Now, it has several advantages. It's working 24/7 at that edge processing, looking for new leaks forming that the negative pressure wave will pick up. And then at the same time, we're configuring it to sample data at specific intervals, let's say when the pipeline is a bit quieter at night, and that will then collect flow and hydrophone data for the ability to look for any existing leaks on the pipeline. The reason we use edge processing and the reason we're getting the internal circuit board to do most of the work is the issue of communication. So some of these pipelines, the water are in remote locations. 4G isn't easily available everywhere, and we want to keep the cost down of transmitting data. So that means the device will only transmit when it suspects a potential leak is present, and then that gets sent to a portal, and we can analyze that data effectively. So finally, I just want to summarize, as we know, we've probably given you quite a lot of information there, but hopefully we can cover it in a bit more in the Q&A. But in essence, what we're trying to show you today is the importance, firstly, of that high frequency 60 Hz data. It provides you that massive, deeper insight into your pipeline, not just in terms of leak detection, but being able to see that if your pumps are working correctly, any potential air valve issues, and also we can confirm if any of your valves are passing. The advantage of edge processing built into the hardware means that we can mitigate the potential issue of communication. All the solutions we talked about today are 24/7 leak detection. So that means once this is implemented, it's providing 24/7 monitoring on the pipeline itself. And it's also working in all operational conditions. So it's working when your pipeline's running, it's working when your pipeline's shut in, and it can even detect leaks when you're doing operational changes as well. We have multiple power and communication options, and we have multiple hardware solutions so that we can provide a robust retrofitted solution to your pipeline as well. Thank you very much for listening, and we'll now take any questions.
Okay, guys, so we're just going to come through to the chat. Just give us a second. So we've got one question that's come through here on the chat. How mature is the water leakage detection market compared to the oil and gas market? I suppose it's not the easiest question to answer, because leak detection in the UK at least has been a regulatory requirement since 1997. So it's you know, it has been around for a long time. It's fair to say, you know, the product, the value of it comes down really to the value of the product with which we're monitoring. In oil and gas, the perceived value of the product is obviously very high. That's driven the way that sector has developed and the amount of engineering that goes into it. We've been around since 1995 in oil and gas, providing leak detection solutions. So I'd say that both markets are mature, but water is inherently more complex, I think, because the different types of pipeline that exist within a single network, the different categories. You know, you've got your trunk mains, your rising mains, then you've got the DMAs, and they all have different characteristics around them, really. So both markets are very mature in different ways. I'd say there's still more opportunities in water, particularly further up the catchment, to undertake effective leak detection. Oil and gas is whilst we're talking very long lengths of pipeline, sometimes tens of thousands of kilometers long per pipe, the approach that you can use there, the actual setup is fairly uniform across different oil and gas pipelines. We do have, of course, differences when we look more at the actual batches of product in the pipeline more closely in oil and gas, which isn't something that's really done in water. So yeah, different horses for different courses. Both sectors are mature.
Probably a bit more investment as well in the DMAs than in trunk and and sewer mains. Right. If we're talking specifically about leak detection, whereas obviously the oil and gas is, in a lot of countries, is heavily regulated, and as we showed in that table before, a lot of oil pipelines can't have leaks present or existing leaks. You know, it's slightly different philosophies, really.
Yeah, I'd go with that. In oil and gas, no leak is allowable, whereas for clean water, at least, leakage is quite an acceptable practice. So we're sort of starting from further behind. It gives us a different challenge, really. Having to find and identify all of that existing leakage. That's where the challenge is, and for us, the approach that we take, that we've taken from oil and gas, which is no leak is acceptable, means we're constantly trying to find new leaks as well as finding background leakage. So we think that brings a real advantage to the water industry by finding new leaks as soon as they form and being able to mitigate the risk of them turning into bursts.
So the next question is, I was wondering, detecting the small pressure changes, does that not elevate the risk of false alarms, e.g. genuine customers filling tanks or farmers drawing from the network? Good question. I think that goes back to my point previously about the importance of hardware with the software. So if you have a network section that's got multiple offtakes or multiple unmetered offtakes, then you need to be able to deploy the hardware in those locations. Otherwise, you're very correctly in saying that if you had an unmetered offtake that a farmer was filling a tank, the leak detection system would see that as a genuine leak withdrawal, because there'd be nothing that it could correlate it to. So that's why you've got to have hardware in the right locations. In terms of small pressure changes, there has to obviously be a learning period when you deploy this equipment, and that's what you do. So the software, the software and the engineers spend time learning how the pipeline operates, and you utilize, and once you start learning that, you reduce the chances of those false positives. But it is a balancing act in terms of where you deploy your hardware and software. If you don't have all the hardware in the right place, you're going to cause false alarms if unmetered offtakes are present on the line.
Yeah, and that's also the reason why we've gone to the effort of developing water-specific pieces of hardware so they can be deployed anywhere along the network where we feel it's appropriate for them to be installed, and that way we can let the algorithms work harder and smarter in identifying what is a leak versus what is an operational event. So yeah, thanks for that question. I think the picking up, you're right. I mean, picking up small pressure changes, but you have to be able to do it. You have to be able to do that to get the insight as to what might be a leak and what might not be a leak. If you don't have that small pressure change, you just don't see any of it.
I suppose one other point just to make on that one as well, if it's an unknown unmetered offtake that you have in your pipeline, as you were just saying, let's say, I don't know, you might have a network and you're not aware that's there, then that would probably class as a theft of water, and maybe that system then has the ability to showcase offtakes that you weren't previously aware of if you have the hardware in the right location. So so thank you very much for that question. So moving on to the next one, can these systems utilize existing instrumentation? Yes, we can. Now, I think in one of the slides we talk about the importance of analog data. So when we talk about leak detection, we're more interested in the resolution and the repeatability of the flow and pressure data, not necessarily the accuracy, because our systems are looking for the changes in pressure and flow. So we can utilize your existing instrumentation. A lot of available flow meters and pressure transmitters can sample at that high acquisition rate. What you have to be careful with is that these pressure transmitters don't have too much dampening or pre-filtering inside them, because ultimately what's going to happen is the sensor's already pre-filtering the data, and then we're going to filter it potentially again, and then you could lose some of that sensitivity you have in the system.
It's also worth pointing out that the whilst we can use existing instrumentation, it also depends where the network that is installed and its capability. So yes, where you've got raw analog pressure data already installed on the network, as long as we can get in and get access to 60 Hz data, then yes, that can be used. But in all likelihood, depending on the complexity of the network, we'd also need to add some other instrumentation as well to help support that. But yes, we can, in principle, we can use existing instrumentation and incorporate that into our package.
Yeah, and yeah, going on to the next part of your question, yes, we can do both. So we were talking about the system being installed in terms of a 24/7 solution, but our hardware and software is designed in a reactive context as well. So if you suspect something's gone wrong on a pipeline, or you suspect one has potentially an existing leak, this type of technology can be deployed. You can find that potential concern, and then it can be moved to another location. So you can have both. I suppose what we'd say is if you have very critical assets, then the 24/7 LGS coverage is probably best. And if you have some other sections of your pipeline that you're not overly concerned about, then you can deploy like the Aquarius, for example, in an offline surveyor mode for so many weeks. We can then look at the data and see if there's anything of concern.
Okay. Coming to the next question from Courtney. How is the innovation work with Wessex and Northumbria Water progressing? It is progressing, as ever, not as fast as any of us would like, but we've hit an awkward time of the year with obviously with the winter and with the weather that goes on. So there've been a few delays in the deployment side of it, but we are on a site sort of level with it now. So yes, it's moving forwards. Likewise, Wessex, we're still working with them on a number of different areas of the network, and that's all still moving positively forwards. So Wessex have indicated that they'd like to continue working with us. So we see that as a positive. Courtney, you also go on to say, do you see the system being a fixed monitoring solution? Oh, sorry, it's just jumped off. A fixed monitoring solution or a portable lift and shift solution? Both. So in any water network, you're going to have your high consequence areas, your strategically important mains, where you want an insurance policy, very much like we see in oil and gas. You need to be proactively monitoring that network, and at the slightest change that might be happening, you need to be alerted to that, so you can go and mitigate potentially what could be worse consequences. So yeah, you very much get that 24/7 permanent monitoring solution there. But at the same time, you can have areas of your network where you suspect you've got background leakage. You can't really drill down to where it is, and this is typically the sort of stuff we've seen with Wessex Water, for example. We can go and deploy the equipment, and we can even deploy it in an offline mode as well. So it doesn't even need to sit there as part of your network. You just take a range of units, drop them in the ground, leave them there to collect data for a while, and then we go and analyze the data from there. So it is worth bearing in mind, because we collect that 60 Hz data, even when an event has occurred, we can retrospectively, and we do retrospectively, go back and analyze that data in further detail. So whilst on the 24/7 permanent monitoring, you would get an alarm straight away, the fact that we can go in and analyze effectively retrospective and historic data in such detail really helps add value and weight to the interpretation of that data from our side. Okay, the next question: can the Eclipse hardware be deployed on HDP pipelines, or is this hardware only used on metallic pipelines?
Well, some of the deployments have been on metallic pipelines, but they can work on plastic. There is a list of certain materials that it can and can't. I can't remember all off the top of my head, but as I said, on the end of the slides there was an email, so if you want to reach out to me, we can provide the Eclipse data sheet and we can go through it. But yes, no, it can work on other material, not just metallic. And it also depends on the configuration we need to deploy the Eclipse in. So it can just be non-intrusive pressure, it can just be non-intrusive flow. We can interchange its requirements.
Okay. Next question. The challenge with algorithms is the ability to adapt in a dynamic network system, with water networks often changing a lot due to resilience requirements. How confident are you on the technology to quickly adapt to the changed configurations?
That's 100%. That's not a major issue. Like most pipelines, even in our experience in the oil and gas, have dynamic networks. You know, variable flow rate, potential multiple injections, multiple receive points. You know, in the oil and gas, we have to handle batch changes and speed of sound, etc. So we can handle that. As I said before, it's about giving the system a learning period. So the longer our system is on, the more information we have on that pipeline itself, and the better we can handle it. And then it's that balancing act in terms of an online LDS, is that you've got to match sensitivity with reliability, because if you make the system too sensitive and you have loads of false alarms, the operators aren't going to use it. So our algorithms can handle dynamic networks. As I said, we can detect leaks in transient, we can detect leaks in static and shut-in. It's just giving the system and our engineers enough time for learning.
Some of the questions that we missed.
Any more we missed? I think we got it. Has anyone got any other questions? You know, happy to on mic and ask if you prefer, rather than using the chat.
Okay, another one's come through on the chat. How could the system be used on an intermittently pumped rising main? Well, fundamentally the same way it works everywhere. The algorithms are able to identify the noise signature associated with that pump, and so we of course would be monitoring the pressure change. We would also be looking at the associated sort of pattern of noise that makes.
Some rising mains are different. Obviously, you might pump it so far and then it's gravity fed after. Obviously, the negative pressure waves principle works on a pressurized pipeline. Flow can work on a slightly lower pressure section. In some rising main capacities, we might only need to put instrumentation at the inlet itself, because if we know where the high point is, any leaks that occur on it, we can reflect that off that high point and provide a leak location. So it's no particular difference. Obviously, pump noise can impact the system, but we do have a set of algorithms to manage that. Any other questions?
Okay, I think one more. Okay, how market ready is the system and products? Are you still looking for innovation partners? Well, yes, we're always looking for innovation partners. Is the simple answer. I think with any solution, the more experience you get, the better you become, and not just necessarily around the technology, but also around the packaging. How you package and wrap that up as a service to a customer, and obviously each water customer in the UK, each water utility operates slightly differently, and as we look at the international side of things, again, utilities operate differently. So in terms of market readiness, the algorithms, if you like, are already proven. We've been using them and practicing them for decades and having constant revisions of that. So the ability to detect a leak is unquestionable. For us, where there's still a bit more innovation as we go along is the hardware side of it. How we for example, embedding those algorithms and software into the hardware, so we can undertake the processing at the edge and therefore only transmit data as and when an alarm is raised, rather than constantly sending data out at 60 hertz, because the most expensive part of an online leak detection system is in the transportation storage of data. So water networks are more complex, so there's more of them, and we're typically in a sector which has less funding available. So for us, that innovation there, is more around the practicality side of it. How we reduce the cost of sending data. So there's, as ever, I mean, we're almost market ready with that stuff. We would definitely like to keep on working with more water utilities, and as many as we can, because you'll each have your own set of challenges and the more insight we get to those, the more we can sort of engineer those out as part of
and talk about trials, etc. Obviously, we've been talking quite a lot about detecting new leaks, and obviously, the holy grail is obviously being to detect all your potential existing leaks on your network. I think a big point to say is if we do deploy this technology in terms of like a trial, etc., you have the ability to what we call doing calibration leaks. So if you pick a pipeline section where you have air valves or hydrant points, what you can actually do is let us install our hardware and software, and then you can go about, don't tell us where your hydrant points are, and deploy several leaks. And that's the ability to prove to you that the algorithms are working. And then, of course, if that pipeline section potentially has any existing leaks, then we can also look at trying to locate them as well. But that's how it works in the oil industry, specifically if our technology is installed, and that's how they test that our system is working. They go to a place that we don't know, and they will generate different leaks, different leak size and different durations, and then we present the results to them.
That fundamentally forms part of the commissioning process for oil and gas, because no leak is permissible. You can't just wait for a leak to naturally occur. So they need to have the confidence that the system will detect a leak as soon as it starts forming. Okay, I hope that answered your question, Courtney. Does anybody else have any other questions? If so, come off mute and just shout them out. Otherwise, we'll bring the meeting to a close. Okay. Well, I think that's it. So thank you very much, everybody. Thank you very much for your time today. If you do have any questions that you weren't able to ask in the forum today, please do drop Harry or myself an email, and we can get in touch with you, and we can take these conversations offline. Okay, but for now, thank you very much.
Thank you very much, everyone.
We'll see you soon.